we're sort of moving on into the next part of our proof section by talking about another method of proof, which is proof by contradiction. So let's start with a little bit of an investigation. So let's talk about this statement here. If n is an integer and 5n plus 2 is even, then n is also even. And we can prove this directly. So if 5n plus 2 is even, that means I can write 5n plus 2 as 2 times some integer k. Well, that means I can write 5n as 2k minus 2, right? Our goal is to show that some integer k actually exists for this. So we can actually still show that 5n is also even, correct? We have 2k minus 1, so now I'm still showing that it's 2 times something to make even. So that tells us that 5n is even. Well, does this tell us that n is even? Sure it does, because an odd number times an even number always gives me an even result, right? 3 times 2 is 6, 5 times 2 is 10. I'll just say that odd times even is even, and we know this to be true, and we can, at this point, now we know how to prove it to be true. Great, so we can do this directly. Well, let's assume that n is an odd number for a minute, and we'll try to rewrite this expression the same way. So 5n plus 2, if we have an odd number, well, we're going to call that odd number 2k plus 1, and again, that's for some integer k. So we'll stick with this expression, simplify our expression, and explain why this can never be even. So let's show that this is not even, this number that we've come up with here. So we have 5 times 2k plus 1 plus 2. If I do all my distribution and my combinations, my addition, I get 10k plus 7. So let's see if we can try to show that it's even. Let's just see what happens here. Right, my goal, if I'm trying to actually show that it's even, if it can never be an even number, I should be able to run into some kind of an issue. So I should be able to get 2 times something. Let's see what happens. So to get my 2 times something, well, it's going to be kind of a pain, right? I can't really factor out the 2 times the thing, right? I can mess with this a little bit, though. So let's see what happens. The other way we could look at it is if it's never even, then it's got to be odd, right? So in other words, let's show that it's odd. So maybe I want to show 2 times something plus 1. Well, how can we generate this plus 1? Well, we can do something a little bit funky here and actually split up the 7. So yeah, we can do this. This feels a little bit dirty, a little bit illegal, but that does create the 1 that I need, and it actually allows me to factor out the 2 that I need to factor out as well. So we got 2 times something plus 1. Well, wait a minute. This is odd. Yeah, it's odd. It's 2 times a thing plus 1. So I guess it's never even, right? If I get odd, therefore it can't be even, right? And that's essentially actually what a proof by contradiction is. It's to say, okay, well, let's actually assume the opposite and show that I kind of run into an issue here. And we do this in logic by something called the contrapositive. So the contrapositive is just a way of saying flip both parts of the hypothetical statement and negate them. So if I have if P then Q, then my contrapositive is if not Q, then not P. And if a statement is true, its contrapositive is true also. For example, if it's a Friday, then it's a tag day. If I take the contrapositive of that is to say if it's not a tag day, then it's not Friday. So I just flip the order of the sentence and I negate the two statements. And to prove something by contradiction, essentially what we're doing is using the contrapositive, and we try to prove the contrapositive is true instead. And we do that by trying to force the problem to run into an issue. And that sounds a little bit strange, but you'll see what I mean in a second. And definitely doing this by examples makes a little more sense. So bear with me for 1 minute. When you're proving the statement by contradiction, we want to follow these steps. So we want to identify what is being implied. in the proof. We want to assume that the implication is false. So we're kind of going about it from the back door to say, instead of proving this head on, let's actually go the other way and say, this statement has to be true because any other possible case can't be true, right? It has to be true because it can't be false, is essentially what we're saying here. Once we have that assumption, we can actually just use direct proof. And we want to try to arrive at a contradiction. And usually that contradiction is going to be based on the given information. So that's going to contradict something in relationship to the given information. So maybe if I'm saying you want something to be an integer, maybe your result winds up not being an integer. And that's okay. It doesn't mean you did it wrong. It actually means you did it exactly right, because we're going to say hence or therefore our assumption is false. And this is kind of the formula you'd want to say here. Our assumption is false, and the original statement must be true. And then you would restate that original statement, just as you would in a direct proof. So we're saying, well, it can't be false. It's not false, so therefore it is true. And those are our 4 steps. So I actually want to take you through maybe a slightly more tricky proof, but really the classic contradiction proof. And that's to prove that the square root of 2 is an irrational number. So prove that the square root of 2 is not a rational number. So then our assumption is going to be the opposite. So the assumption, the implication is that the square root of 2 is irrational. So our assumption is going to be that it's not. So I'm going to say assume for contradiction, and I'm going to say that straight out, that the square root of 2 is a rational number. Well, if something's a rational number, so say therefore, I can write that rational number as a fraction of 2 integers. So we're going to say, let's write it this way, and the conditions, of course, are going to be that m and n have to be integers. That's how we define a rational number. And the greatest common factor of those 2 numbers is 1, right? It's a fraction I can't reduce, right? 2/4 we would say is not technically a rational number because I can reduce it to 1/2, which would be, right? So I want a fraction in lowest terms. So we start with our assumption. And now we're going to manipulate this. And this is not entirely helpful to work with, so let's work with something a little more useful, and let's do that by squaring both sides. We're kind of just playing with the math just to see where we get, see where we get with as we go from here. Let's keep playing with this a little bit. So the other thing that's not really helpful is the fraction. So let's multiply everything by n squared so we don't have a fraction. Well, now look at what we've got here. We've got 2 times something. So this tells us that m squared is even, right? Because it can be written as 2 times a number. Because m squared is even, let's let m itself, sorry, I want to back up there. If m squared is even, then m is even also. Right? 2 squared is 4, 4 squared is 16. I can never square an odd number and get an even number. So m is even. Let's use our standard issue even number construction here, 2 times k, where k is an integer. Great. So, well, that tells us that m squared can also be written as 4k squared, right? M squared. Actually, let me show you that. So 2k squared, 4k squared. Well, if m squared is equal to 2n squared, just like I have up here, and m squared is also equal to 4k squared, then I should be able to equate these 2 things, right? So 2n squared is going to be equal to 4k squared, and I'm running out of room, which means that n squared can be written as 2k squared. So I'm dealing with m and n in particular, right? Well, that tells us that n squared is also even, which means that n is even. this is a problem. Here's our contradiction. And this might have been a lot that I went through really quickly. If both of these numbers are even, then their greatest common factor is 2. And 2 is not 1, which means this fraction can be reduced. And this is a contradiction, right? It contradicts our given information, right? If something is a rational number, then the greatest common factor between the numerator and denominator should be 1. And it's not. And that's okay. That doesn't mean we did it wrong. It actually means we did it exactly right. So now we're going to say, therefore, and I don't really have the room here, our assumption is false. So the given statement must be true. And I'm not going to write it because I don't really have the room here. And I'm going to say one more, therefore, square root of 2 is irrational. And then we're going to use our little box like we always do to end our proof. And I know I just crammed that into not a lot of room. But there is your proof by contradiction.